Hey everybody, welcome to PC Perspective. I'm Ryan Shrout, joined by Alan Malventano. Good to see you. Not that I haven't seen you all day here at the office, but whatever. We're setting up the stage. So we're here today to talk a little bit about VR benchmarking, and in conjunction with the release of the HTC Vive. So HTC actually sent us a review unit of the HTC Vive. We've had it for a handful of days, and we got an Oculus Rift on day one. And one of the first things and one of the first issues we came up with is, how are we going to evaluate these in the way that we're used to evaluating things, right? We measure performance, we want to measure experiences, but we're also very, I think, one of the unique outlets that tries to very closely match an experience to a performance metric or performance heuristic, or whatever you want to call it. And with VR, that's very difficult. And I wrote up a story that went up today on PCPer.com titled "Measuring VR Performance and Experiences: A Prologue," and the fancy name basically is saying like, this is just the beginning for us. Like, it's just we're just kind of starting out, but in the way we did it with frame rating originally, it's like, okay, we're actually going to write about and kind of talk about our process as we go. Input from developers and the community and hardware vendors is still very important, so we wanted to get this kind of conversation going with as many people as possible. So what makes, I think the first thing that we want to tell everybody is basically why measuring performance in VR is so different than measuring performance in the games that we have today. Measuring games on a PC on a standard two-dimensional flat screen or slightly curved game scenario, gaming PC is not simple, but it's become defined or almost perfectly well defined, right?
Sure, yeah.
We have tools like Fraps, you have tools like PresentMon, you have tools like FCAT, you have tools like frame rating that all kind of combine to give you different angles of the story that then you can evaluate and modify and massage so you get the kind of story that you're looking to tell with the data. And a lot of that depends on two things. One, being able to know exactly when a game engine is done with a frame. It's called a present time. And the other one is the more recent thing with frame rating and FCAT is that we know when that frame is displayed on the screen. We've talked about it before. If you haven't done research on what frame rating is or FCAT is, we'll put a link in the description here to the story that's like, what was that, 2012, 2013, 2012, right? Where we first started talking about how the overlay works and how we measure and capture directly.
But the short version is just you're trying to replicate, like, what do you actually see on the screen?
Yeah.
And the closest you can get to that is to actually just capture that data that's going out to that display.
Which we were able to figure out how to do. Yeah. It took a lot of work, a lot of technology and software to do it, but we figured it out. Now with VR, things are different. One, we can't capture the output to that the user actually sees in their head-mounted display.
And there is an output that goes to the screen, but that is not necessarily the same as the output that goes to the...
And it's definitely not the same, right? Because the image that gets sent to your head-mounted display, whether it be a Vive or a Rift, is, it's malformed, not malformed, but it's morphed, right? So that the lenses can correctly correct it back to your field of vision. So we can't capture that. We've tried to. We've tried to directly capture what's coming out of
capture it poorly with
from
the
the PC to the head unit, but it doesn't show up as a display. The Vive and the Rift show up as these kind of mystery hidden devices that the only thing that really has direct access to them is their associated SDK. So the Oculus SDK can access the Rift, and then OpenVR/SteamVR can access the Vive, and there's some interoperability. We're not going to get into that discussion here, but headsets may work on multiple platforms, as it turns out. So we can't capture it. That's unfortunate. But what does get output to what they call the companion screen, or the viewport, is some version of that. It could be a single eye in a column type style where it's very tall rather than wide. It could be something that they've morphed into 16:9. It could be something that they've just cropped out of one of the eyes. So what we can do with that is we can measure how many times that is drawn to. So that's one data point. We can measure the present. We can't any longer measure the present from the game to DirectX because the game doesn't talk to DirectX.
Right.
The game actually talks to the VR virtual reality SDK. So it actually submits its frame to OpenVR or Oculus SDK, and then it is responsible for communicating to DirectX, communicating to the GPU, and then actually outputting to the screen. With Oculus, it's still kind of a black box for us. We're working with certain people inside that company to get access to more information. But with SteamVR, you don't have to dive very deep into the options to find a performance tool in there. It's obviously meant for developers, but if enthusiasts want to mess around with it, at this point they haven't taken it away. And so if you look at this page of our article, you see that we're looking at a massive amount of data that encompasses all of these different data points, registering from present time to submit time to application GPU, all the way down to like these wait get poses called. If you look over here, you'll see like there's like negative times that you're dealing with, and it can be hard to kind of wrap your mind around. Negative times are
things
like
that are happening before the frame is ready.
The frame gets started.
Yeah.
Right. Like this is get poses is essentially like where's all the hardware, where's the headset, where's the controllers, whatever it is that it's trying to monitor. But you can see if you look at that graph, there's just tons of data to output here. All of it very interesting, but all of it also, or most of it, not completely understood at this point, like how it affects the overall chain.
Right.
The one we're interested in for this particular story is total GPU.
What is it we're trying to test specifically?
So we're just trying to measure performance of GPUs.
Okay, in VR.
In VR. Like I want to go through this typical stuff that we talk about, like, okay, the 980 Ti versus the Fury X, or the 970 versus the 390, which one plays VR game X better, right? And even in that case, is like, let's translate that to an experience for the user. Does one GPU get you a better experience? So if we look at total GPU on that is actually the total GPU render time in milliseconds. So similar to what a frame time is, right? If you know, 60 hertz is 16.6 milliseconds, 90 hertz, which is what your HMDs update at, is 11.1 milliseconds. Your total GPU render time is the amount of time the GPU takes to render all of the work for that particular frame, right? So that's another data point for us to look at. So good stuff there. Now the game we're using for this kind of first discussion point is called The Gallery, Episode 1, Call of the Starseed. A very long name.
Very long name.
But when I started to inquire with some people, what's the best looking VR game you've seen? What's like the most kind of graphically intense VR game you've seen? Because a lot of them have been very cartoony and stylized. This name came up a couple of times. Is developed by Cloudhead Games, and it looks really, really good. It's stunning. There's a lot of lighting effects. There's a lot of special effects. The gameplay seems excellent. There are image quality settings in the game, presets for low, medium, high. You've got individual settings for shadows, depth of field, lens flares, aliasing, anti-aliasing, not aliasing. You probably don't want to enable aliasing.
And it is probably the most demanding graphical game we've seen yet so far for VR.
It is. Right? It is. So it's pretty impressive. So that's one we kind of use to set the ground floor for what can we possibly do, and then kind of expand that out into other titles.
Right.
So the first thing we did was we just started kind of combining these different data points and seeing what we got interesting out of it. So here is a result. These are all run on the HTC Vive on a GTX 970. This is actually on our $900 VR system build if you want to go back and look at the total specs for it. GTX 970 in the gallery on a low preset. This is what the game recommends for the GTX 970 equivalent class graphics card, is that preset.
Sure.
Now what you'll see here is the orange line here is your PresentMon frame time, right? This is actually measured by PresentMon, very similar to what Fraps does, and it's giving you the frame times, not of the game into the SDK, but of the SDK to the viewport window, to the companion monitor display.
So the thing that goes to the headset?
No, the thing that goes to the monitor.
Oh, okay.
We can't measure what goes onto the monitor. That's kind of hidden behind all of the secret stuff that Oculus and OpenVR are doing. This measures what you'll see on the screen.
But in our case, for that particular game, we were able to use a display that also went 90 hertz.
Right.
For refresh rate.
Yep.
And since we're matching both of those, and again, this particular game just happens to be able to go all the way up to 90 hertz, being displayed on the regular display connected to the PC, right? So we're kind of able to, we had an advantage for testing for this particular game.
Yes, and it's important to note, like on a 60 hertz display, this data didn't look this way. It kind of sat at 60, and we went to 120, we had other issues, right? So we had to find a monitor that had a refresh rate that allowed us to match what the refresh rate of the HMD is, giving the SDK the best possible chance to duplicate the information between what it's sending out to your head unit and what it's sending out to your companion monitor, right? The monitor on your desk. So the orange line, there's a lot of variance there. It's not a very smooth line necessarily.
Sure.
But that is, again, part of the VSync back pressure getting put into a game time, right? So if you notice, it is centered on about 11.1 milliseconds, which equals out to 90 frames per second in the grand scheme of things.
In this particular case, like what we actually saw on the display looked like a fairly smooth. Like
it was.
90.
It was very smooth.
Yeah.
Yeah.
So when you see these spikes here, it wasn't really.
Yes.
It wasn't visual.
Right. This is equivalent to data you would get from Fraps, not data you would get from frame rating or FCAT.
Right.
And so the variance doesn't necessarily equate to what you're seeing on the screen, but it is a good threshold of things to look at. Now, the blue line is total GPU render time from the same test run. And you'll notice there that it is ranging between, I don't know, let's say 6 to 7.5 milliseconds, which doesn't give you anything about necessarily what frame rate you're going to run at, but that it's below 11 milliseconds.
Yep.
And thus, the entire game is able to run at 11 milliseconds or under and maintain a 90 frames per second experience, which is what we saw in the headset when we were playing it as well, right? So if
both the headset and the display in this case, like there is no VSync off, first of all, for VR.
There is none, right?
Right. Everything is VSynced. And it has to be. You would really tearing would really look bad on a VR headset, right? So that's just important to keep in mind because as you can see, like the next drawing down or the next chart down, becomes very apparent what happens once you get too close to that amount of time, right?
So this is the same GTX 970 in system, but we just basically turn the image quality up from low to high, right? Again, this is against the developers' wishes. I don't want them to freak out because we're showing the game kind of having a poor
They don't recommend
scenario.
you to play it at this.
Right.
Yeah.
And so what you'll see here is we have a section that's running at 22.2 milliseconds, and then a section that's running at 11.1, 22.2, and 11.1. And we're doing this on purpose. We found an area where if you're looking at a campfire, it's a tough rendering object, and so it slows things down. You're running at a lower frame rate, and thus you're running at 45 frames per second or so. And when you look at it in the screen, it looks like it, when you're looking at it in the head unit, it looks like 45 frames per second. We can tell a difference in the animation smoothness between section 1, 2, 3, and 4 in that. Now what's interesting is we correlate that with the total GPU render time, the blue line again. Notice that when we are looking at the campfire, this first section here, that the frame time is right about 10.5 to 11 milliseconds. When we drop down to looking at the skybox, where the frame rate goes back up to 90, the GPU render time drops back down into that 7 to 8 range, right? And it goes up again as we look at the campfire and down again as we look at the skybox. Now,
we're going to cover this more in detail in a couple minutes, but like it's important to note that what you're viewing through the headset that entire time, that those displays are still refreshing 90 times a second.
They're not variable refresh rate displays.
And if you're moving your head around, that still looks smooth. It's not like the game suddenly makes this go half of the rate of update.
Right.
But we'll talk about that more.
But if you're looking at a thing in the game that is animating, whether
thing that's
fire,
animating,
the little embers that fly off of it, you can definitely tell a difference. So what we take of that is that when your GPU frame time or your GPU total render time approaches 11 milliseconds, it's not exactly 11 because you got to have room for other things to occur, but as it approaches 11 milliseconds, the game may have to, fall back to its next VSync interval of 45 FPS, which is what we saw here.
Yep.
So let's take another example. That's kind of like a worst case scenario. You've got a modestly powered GPU. You've turned up the image quality settings. What if you said, okay, well, I actually have a 980 Ti and I want to turn everything up to high. What can I get out of that? And this is the result you get here. Now, we still see a variance in the GPU render time. Notice that as we're looking between the fire and the skybox, right? When we're looking at the fire, we're taking like 8 milliseconds total GPU render time.
Sure.
And when we're looking at the skybox, less than 5, right? So you're seeing a big performance improvement from the 970 to the 980 Ti, which you'd expect. But because even in the worst case there, you're only hitting 7.5 to 8 milliseconds, you're not getting to that 10 to 11 millisecond mark, and thus the game can run at 90 frames per second all the way across there, right? You're going to stay at that 11.1 milliseconds. Your experience is going to be perfect kind of all the way through, and that's what it was when we looked through the headset, right? It was you could tell a noticeable difference immediately. So what's interesting here is that the correlation between the performance we saw in the viewport / companion monitor matched what we saw in our headset which matched with our GPU render time.
Yep.
Right? Giving us the idea that, hey, this GPU render time could be a very important metric for us to hold on to going forward. Now, there's a couple of other comparisons we'll go over real quick. Here is the 980 Ti versus the 970, looking at it. And this is just basically how would we potentially compare two graphics cards directly, right? You can see how you could do it, right? The blue is the 970 and the orange is the 980 Ti. Clearly there's a performance delta, and clearly as we approach this 10 millisecond mark in the blue, you think, okay, we might be too strenuous for this GPU, for this game, for this image quality settings.
Right.
Whereas the orange line doesn't really come across any of those. These graphs did not load, so I'm going to let that reload for me there. There we go. This is the 980 Ti versus the Fury X.
Yep.
They're very similar. They're much closer than the last graph we just looked at.
They are. Lower is better.
Lower is better because these are frame times. So the 980 Ti is a little bit better when looking at the skyboxes. These sections down here, right? But both these cars seem pretty even.
They end up leveling out.
Fire.
Yeah, the more complicated scene, they end up leveling out.
Yeah. And then the 970 versus the 390, just for good measure, shows that the GTX 970 is a little bit faster when looking at the fire and maybe a little bit slower when looking at the skybox, right? So this, again, not concrete final answers. We haven't looked at a whole bunch of GPUs or different scenarios in this game, but this is giving us an idea of how you could directly compare GPUs with this tool set and kind of going forward.
Something interesting that comes out of all this data is that, like, in the case of the 980 Ti versus the Fury X, like, as long as both of those cards are staying below 11, the end result, there is no difference in the game. There's no visual difference, like, because the VR systems right now are only running at 90.
Yep. That's a very good point.
Yeah, it's as long as you can stay below that threshold at whatever settings you want to run it at, it's identical. It's an identical experience.
So if you look at this graph again, both of these GPUs seem to stay below that like magical 10 millisecond mark, 10 and a half or whatever it happens to be, whatever the cutoff is for this particular game. So these two GPUs would perform the same in VR. Yep. In this particular scenario. Very good point. So that's that's where we're at in terms of how do we potentially measure stuff. Now there were a couple of other scenarios that side effects, experience matching that we wanted to talk about. One of them is that we could see something called pull-in.
Okay.
Which
do that one first.
Which is, well, this is how I've ordered them in the story, right? If you're looking at the right place at the right time, if you're looking in the direction of a rotation, you can see something called pull-in.
Yep.
Where the side of the display shows like an encroaching blackness, if you will, encroaching black line that gets a little bit closer.
You have to really be looking for it.
You have to struggle for it, for sure.
Yeah.
And the side effect of experiencing two different refresh rates or two different animation rates at the same time in the same scene in the same environment, right?
Which you would think would be jarring, but you have to be looking for it. We found. Like we're used to seeing it now that we've like discussed it a lot and everything.
I don't know. I would disagree that it's really super hard to find because if you know we had to wave our hand in front of our face, but if there was something else happening in the scene,
sure, it would be happening at a
let's describe what we're talking about here. If you looked at the GTX 970 at the high quality preset, again, this is our worst case scenario where we are forcing the system in the game into like a 45 FPS mode.
Yep.
By looking down at the fire. If we took our avatar hand and we
just kind of flailed
it around like a crazy person in front of our head unit, just so we could make sure we could see it, right?
Yeah.
The game is running at 45 frames per second. So the hand is updating and running at 45 frames per second. But your display is running at 90 hertz.
Right.
So if all of that just in any scenario with any kind of display, whether it be a virtual reality display or a typical display, you would essentially get every other frame, every other refresh would get a new frame.
The scene changes.
And you would see the hand slightly animate in a certain way, right?
And it's similar to as if you were running a just a regular desktop display, V-synced.
Yes.
At 90.
Yep.
Right. But the difference here, though, is that we're panning across while we're moving the hand around. And the reason we did both of those things was to demonstrate that your view, you moving your head around, that is fluid and remains fluid at 90 frames per second of worth of changes. So that, in other words, even if the game engine is bogged down and it's doing things slowly, you moving your head around in the scene still looks just as fluid regardless.
Up to a certain point, I would guess.
Up to a certain point, but yeah, it's basically like, the scene could be going 45 frames per second. That doesn't mean that all of a sudden your perception of reality through the headset changes.
So what I would think is, if you look at this sample YouTube video we put together that kind of has the hand animating, the important part I think to realize is if you look at the 970 with the super slowed down version of it, you'll note if you watch the pan across versus the animation of the hand, the pan across the screen will appear to be smoother than the hand animating in the space. And that's what we're talking about when we say, hey, how do you experience two different frame rates or refresh rates or whatever you want to call it, animation rates I think is probably the best way to put it, on the screen at the same time. Right? The 980 Ti doesn't have that issue because everything's running at 90 frames per second. Right? But when you have this weird thing where you're running at 45 and the game refresh rate of the display is still 90, this is when you can run into it. And so how does that happen? What's the magic that happens
that lets you continue to pan smoothly while the game engine is actually bogged down?
It's called time warp. Right, and
this is... Are we going to do that
again? No. It's called time warp, and it's basically the idea that SDK is that Oculus or Steam VR SDK is getting in our way of measuring things really the way we want to, is
also doing magic.
Intelligently saying, oh, I'm updating every 11 milliseconds. Okay, well, it's 11 milliseconds, and in the game, you didn't give me a new frame. You're behind. Well, I'm going to make this user's experience a little bit better. And I'm going to take that last frame that you gave me, maybe you sent it again, but I'm going to take the same frame that I last displayed, and I'm going to shift it ever so slightly in the direction of the user's head movement. Right? So if you're turning to the right, the frame is going to move slightly to the left. And it's not just guessing, it's basing that on the tracking information from the headset.
And it's not even just a simple shift, it's actually like if you were rotating a globe. It's like it's a warp. It's an actual warp.
It's probably applying it to a 3D structure and doing a warp and So it basically shifts the image a little bit to the side, and thus it appears that things are updating smoothly for you. But and it will do that as often as it needs to, kind of like within reason, so that you don't have like the sweeping black line across your display.
And then hopefully the game engine will have another rendered frame that's actually at that new direction of view.
So after it does this kind of warping, it says, okay, game, I'm actually at this location now. So it's sending updated location data back to the game. It will now have a new frame ready at the next iteration, hopefully, otherwise you're dropping frame rates to another step down. And you'll kind of be in this pattern. If you're staying at 45 frames per second, you'd have this kind of back and forth pattern. And we actually have a video of that. And again, this is another one's kind of hard to see, but if you look on the right-hand side where the green and red lines are, you'll see that the edge of the black line kind of alternates back and forth between them. And that is the pull-in effect, as it's called. John Carmack called it that when he was tweeting at me about this phenomenon, the pull-in effect of the image during that rotation. Now, Alan and I, we could see it with our eye if you try to see it. You have to
we had to use a different kind of camera just because like a regular camera couldn't get that sharp of an angle. You really have to be looking at the far right of the...
If you're a human, which all of us are, maybe, you look to like the direction you're turning, you turn your eyes all the way to the right, and then you move very quickly, and you may see this like black encroachment. It's very hard to see.
The only way that we noticed it, I didn't notice it in actual use at all.
Until I said something to you about it.
And then it wasn't until like, okay, how does this time warp thing actually work? Let's try to figure this out. And then, we did some research, and then I had to like do a thing where, look, because normally if you look to the right and you start to turn your head, like you're still looking at that thing that you were trying to look to your right on. So you pretty much almost immediately move away from where the pull-in would have been, right? So you have to kind of, almost force your eye to stay to the right and flip your head to the right.
And even when you do it, you're only seeing it in your periphery.
And it's only for a split second too. So.
But it's
very impressive that it can manage to do all that.
It's the magic that allows, even if your game is missing a frame or two here and there, or you're at static 45 frames per second, like we are in this scenario, that it's still, like your panning still moves smoothly. Now, if you're doing a bunch of stuff in the game, it's like, your hands are moving, you're shooting.
That will slow down.
There's people moving, there's enemies moving around or whatever it happens to be. Those will still run at the lower frame rate, the game refresh rate, because no magical SDK is going to try to interpolate where those objects may be and try to repatch the image. It's like it can't do that. It's taking the whole image and it's able to shift it and warp it in essentially 4 directions. Right?
Or if you're like on a vehicle in a scene and you're looking out like the side, like the window of a train or something, right? And you're looking out it, and if it's rendering slowly, that will be
it won't be able to fix that.
Right, and it might even be juddery depending on how, like VSync judder kind of a thing, right?
So that's kind of where we're at with this, guys. We don't have any firm conclusion. We're not here to tell you like NVIDIA's graphics cards are better or AMD's graphics cards are better. We're really just getting started with it. I think we have a solid ground now to stand on and go forward, at least on the Steam VR side with HTC Vive. We don't really have those same options on the Rift yet, and hopefully this discussion and the story and the stuff we're putting out there will help allow them to get us kind of easier access to some of those SDK capabilities. And from there, we basically start this whole process, right? Let's get some video cards down. Let's get some game scenarios down, and find areas where performance matters and is interesting. But I think it's pretty interesting what we've been able to do so far, and it's not just a simple let's run piece of software and report what that average frame rate is or something like that.
The average especially now that you're on this thing where it's a threshold for 11 milliseconds, like that you cannot use average at all.
There was a point, I want to say where it was, I actually talked about that in the story, where the average for the 970 at high is like 107 frames per second.
Sure.
Right? But because of when those dips are way under that, right?
And what they
below
cause.
90, because as soon as you drop below 90 or 11.1 milliseconds effective, you're going to drop half of your frame rate because of VSync. That it's much more important to look at these things holistically, looking at the multiple data points that we're looking at, and then making sure that you're matching it to an experience for the end consumer as well. So be sure to go to PCPer.com. We'll have a link in this description for the full article. Again, that title is Measuring VR Performance and Experiences, a Prologue. We may never have an epilogue, but we may have the middle part. I don't know what that's called. Is that just a log?
Don't know.
Pro, epi, we'll have the middle
words
part.
In the middle.
The words for the middle. Ongoing for probably well many years into the future. So thank you guys for watching, and hope you found it interesting. Thanks.
Thanks.
If you enjoyed this content, consider supporting in-depth technical content by contributing at patreon.com/PCPer.